September 5th, 1977, Cape Canaveral, Florida. Pad 41. A Titan III rocket is sitting on the launch pad. Bolted inside the upper stage is a spacecraft about the size of a small car. Gold foil, antennas, and strapped to the outside, a phonograph record. The countdown hits 0, the rocket lifts off, and within seconds, something goes wrong. The second stage engine shuts down early. 1,200 pounds of fuel still in the tank, unburned. The upper stage, the Centaur, picks up what happened. Its onboard computer does the math, recalculates, and orders a longer burn to make up the difference. It fires until there's almost nothing left. When the engine finally cuts off, the Centaur has 3.4 seconds of propellant remaining, 3.5 seconds. That's what stood between Voyager 1 and a piece of space junk tumbling back toward the Atlantic. That was 49 years ago. Right now, Voyager 1 is 25.7 billion kilometers from Earth. If you sent it a message at the speed of light, you'd be sitting there for 23.5 hours before it arrived. By November of this year, that wait stretches to a full 24 hours, one light day. No human object has ever been that far from home. It's heading toward a star called Gliese 445. It'll arrive in about 40,000 years. Everyone who built it will be long gone. So will everyone watching this, and bolted to its side, that golden record is still there. Greetings in 55 languages, the sound of wind and rain, a mother's heartbeat, Chuck Berry playing Johnny B. Good, a baby laughing, all of it hurtling through interstellar space at 61,000 kilometers per hour with nobody to play it. If this is the kind of thing you think about at 2 in the morning, hit subscribe. We go deep here. But here's the thing most people get wrong about Voyager. They think it left the solar system. You've seen the headlines. Voyager exits the solar system. It's been on every news site. It didn't, not even close. What Voyager actually crossed, and what's still waiting out there beyond it. So far away that Voyager won't get there for another 300 years. That's what this video is about. Ask most people where the solar system ends, and they'll point to Pluto. And honestly, fair enough. For 76 years, Pluto was the last planet on the map. Then, in 2006, the International Astronomical Union voted to demote it to a dwarf planet. Everyone got angry. The debate still hasn't died. But in July 2015, NASA's New Horizons spacecraft flew past Pluto for the first time. And what it sent back was way more interesting than the argument over what to call it. Glaciers, not water glaciers, nitrogen ice glaciers, flowing across the surface, mountains made of water ice, frozen so hard in the cold that it behaves like rock, rising 3,500 meters. A heart-shaped basin, 1,000 kilometers wide, where the nitrogen ice is slowly churning, convecting, like the surface of a pot that hasn't quite started to boil. Pluto isn't a dead rock at the edge of the map. It's a world. A frozen, strange, still-moving world. But here's where it gets interesting. Pluto orbits the Sun at about 30 to 50 astronomical units. 1 astronomical unit is the distance from Earth to the Sun. 150 million kilometers. So Pluto sits 30 to 50 times further from the Sun than we do. Sounds far. It is far. But the actual boundary of the solar system, depending on how you define it, might be 200,000 astronomical units away. Pluto isn't the edge, it's the doorstep. We haven't even left the porch. Past Neptune, from about 30 astronomical units out to roughly 50, there's a region called the Kuiper Belt, a ring of frozen debris, hundreds of thousands of objects bigger than 100 kilometers across, and trillions of smaller ones. Most of them have been out there, untouched, for 4.5 billion years. They formed when the solar system formed, before the Earth had an atmosphere, before anything was alive anywhere, and they're still sitting there, dark, cold, exactly where they were left. On New Year's Day, 2019, we got our first good look at one. New Horizons, the same spacecraft that flew past Pluto, reached a Kuiper Belt object called Arrokoth, used to go by the name Ultima Thule. At that point, it was the most distant object a spacecraft had ever visited, and when the images came back, the scientists just stared at it. It looked like a snowman, 2 lobes, one bigger than the other, connected by a narrow neck. Alan Stern, the lead scientist on the mission, looked at the first image and called it a snowman. Will Grundy, one of the co-investigators, said later it reminded him of a raspberry, like it's made of little subunits, he said. That wasn't just a cute observation. The larger lobe is covered in mound-like structures, each about 5 kilometers across, and they all look weirdly similar, same size, same shape, like building blocks that clumped together to form this thing billions of years ago, and then just stopped. In February of this year, a researcher named Jackson Barnes at Michigan State University published a study that finally showed how it happens. He ran 54 computer simulations of the early solar system. What he found? When a cloud of tiny icy pebbles collapses under its own gravity, it doesn't form one blob. It splits into two. Those two clumps orbit each other, spiral slowly inward, and eventually touch gently, about 6 meters per second. Walking speed, not a crash, a drift, and once they make contact, the shape holds for billions of years, because in the Kuiper Belt there's almost nothing to disturb them. No collisions, no close encounters, just cold and deep time. About 1 in 10 Kuiper Belt objects are shaped like this. Contact binaries, frozen mid-formation. They're not rubble. They're fossils of the process that built planets. And there's something else. A 2024 study found that objects like Arrokoth may still have ancient ices sealed inside them. Carbon monoxide and other gases, trapped since the solar system began. If one of these things ever gets knocked loose and falls toward the sun, those ices warm up. The gas builds pressure under the surface, and the whole thing can blow apart. Quiet for 4.5 billion years. Then, without warning, an ice bomb. But the Kuiper Belt, as big as it is still the sun's neighborhood. Everything here still orbits the sun, still follows the rules. To find the actual edge, you have to go a lot further, and what you hit out there isn't a place on any chart, it's a wall. The sun is loud, not in a way you can hear, but every second of every day, it's throwing charged particles outward in every direction. Protons, electrons, racing away from the surface at speeds up to 800 kilometers per second. This stream is called the solar wind. And it doesn't just fade into nothing, it pushes past Mercury, past Earth, past Jupiter, past the Kuiper Belt, pushing outward, inflating a bubble around the entire solar system. That bubble has a name, the heliosphere, and everything inside it, everything the solar wind touches, is still technically part of the sun's territory. The heliosphere blocks most of the cosmic radiation that floods through the rest of the galaxy. You're inside it right now. It's the reason your DNA isn't getting shredded by galactic cosmic rays every second of the day. So what happens when that wind finally runs out of push? It hits something, the interstellar medium. Gas and dust and plasma drifting between the stars. The sun's wind slams into it, and at the point where it can't push any further, the wind drops from supersonic to subsonic instantly, like a shockwave in reverse. That boundary is called the termination shock. Voyager 1 hit it in December 2004, 94 astronomical units from the sun. Voyager 2 crossed it in August 2007 at 84 astronomical units. Same boundary, 2 different distances. 10 AU apart, which means the sun's bubble isn't even round. The galaxy is pressing on it from one side, squishing it, like wind leaning on a soap bubble. But the termination shock isn't the edge. Past it, the solar wind keeps going, just slower now, denser, hotter, piling up against the incoming interstellar wind. This messy, turbulent zone is called the heliosheath. In 2008, NASA sent a small spacecraft called IBEX to map this region. When the data came back, nobody knew what to make of it. There was a ribbon, a narrow band of energetic particles stretched across the sky, 2 to 3 times brighter than anything else on the map. It wasn't supposed to be there. The best guess is that solar wind particles are bouncing off the interstellar magnetic field and getting reflected back. But even that doesn't fully explain the shape. We mapped the border of our own solar system and found something we can't account for. Past the heliosheath, there's one final line, the heliopause, where the sun's outward pressure exactly equals the inward pressure of interstellar space. Past this point, the sun's wind no longer reaches. Its protection ends. August 25th, 2012. The data trickles into JPL at 160 bits per second. slower than dial-up. It takes almost a full day to arrive, but when the team sees it, there's no ambiguity. Galactic cosmic rays spike upward. Solar wind particles drop to zero. The magnetic field swivels, no longer pointing back toward the sun, but aligning with the galaxy. Voyager 1 had crossed the heliopause. It stepped outside the bubble, 121 astronomical units from the sun, and then, out there, in the space between stars, the plasma wave. Instrument picked something up. A faint, steady vibration. Not a signal. Not a message. Interstellar plasma, humming, oscillating in the void. The space between stars is not silent. It hums, so that's it, right? Voyager left the solar system. End of story? No. Because past the heliopause, past everything Voyager has crossed, there is something else. Something so large that Voyager, moving at 61,000 kilometers per hour, will not reach its inner edge for another 300 years, and nobody has ever seen it. In 1950, a Dutch astronomer named John Oort was sitting with a problem he couldn't let go of. Long-period comets. The ones that swing through the inner solar system once every few thousand years, sometimes once every 100,000, and then disappear back into the dark. They come from every direction. Not along the flat plane where the planets orbit. From above, below. Random angles. Like they're falling inward from a sphere. Oort tracked the orbits of 19 of them. 10 were first-timers. Comets visiting the inner solar system for the very first time. And they were all coming from roughly the same absurd distance. Around 44,000 astronomical units from the sun. His conclusion? There has to be a cloud out there. A vast spherical reservoir of icy objects. Trillions of frozen leftovers from the early solar system, kicked outward by the gravity of Jupiter and Saturn billions of years ago, and parked in the dark ever since. That cloud is named after him, the Oort Cloud. Nobody has ever directly seen it, not one confirmed object. Everything we know about it comes from the comets. It occasionally drops into our neighborhood, but the math keeps landing in the same place. A shell of icy bodies, starting somewhere around 2,000 to 5,000 astronomical units from the sun, and stretching outward to maybe 100,000 astronomical units, maybe 200,000. That outer number, 200,000 astronomical units, is 3.2 light-years. Proxima Centauri, the nearest star to the sun, is 4.2 light-years away. The Oort Cloud may reach more than halfway there. Let that land for a second. The solar system, the thing from the poster on your classroom wall with 8 tidy planets in a row, might actually stretch almost to the next star. Voyager 1, the fastest, most distant thing we've ever built, won't reach the inner edge of the Oort Cloud for about 300 years. Once inside, it'll take roughly 30,000 years to come out the other side. Even light needs 11 days to get to the inner edge from the sun. And what's sitting in that cloud? Trillions of objects, probably. Icy, small, most of them less than 100 kilometers across. Total mass, somewhere between a few Earths and 100 Earths. Nobody can pin it down because nobody has ever observed one in place. We only see the ones that fall. Every so often, something disturbs one. A passing star drifts close enough to nudge an Oort Cloud object out of its orbit, or the slow gravitational tide of the Milky Way's disk tugs one loose. It starts to fall inward, toward the sun, a journey that can take millions of years. And when it finally arrives, we see it as a comet. Long period, random angle, bright tail, then gone again. Up to 90% of the comets that reach us from the Oort Cloud got pushed here by the galaxy itself. There's one object that might be a clue to all of this. Sedna, found in 2004. It has one of the strangest orbits we've ever measured. At its closest, 76 astronomical units from the sun. At its farthest, nearly 1,000 astronomical units. That orbit doesn't make sense using just the gravity of the known planets. Something else shaped it. Maybe a star that drifted past the sun billions of years ago, back when our solar system was still part of a dense cluster of newborn stars. Sedna could be a relic from that encounter, a piece of the inner Oort Cloud, caught in a gravitational no man's land. And this is where the whole thing turns into a question that doesn't have a clean answer. Where does the solar system actually end? If you go by the sun's wind, it ends at the heliopause, 123 astronomical units. Voyager crossed that in 2012. If you go by the sun's gravity, by the farthest point where it can still hold something in orbit, then the edge is the outer rim of the Oort Cloud, up to 200,000 astronomical units, 3.2 light-years out. And if you go by where the sun's pull gets weaker than the pull of nearby stars, the boundary lands somewhere around 2 light-years, roughly halfway to Proxima Centauri. The sun's light, its wind, and its gravity each draw a different line. None of them agree. The edge of the solar system isn't a wall you hit. It's a fade, a slow dissolve from here to everywhere else. Somewhere in the constellation Ophiuchus, right now, Voyager 1 is still flying, 61,000 kilometers an hour, 172 astronomical units from home. The signal it sends back takes nearly a full day and arrives at 160 bits per second. Slower than a text message, its power is fading. The plutonium in its generators has been decaying since 1977. NASA has shut down most of the instruments already. Within a few years, the last ones go dark. The magnetometer, the cosmic ray detector, the plasma wave instrument, the one that heard the hum between the stars, and then Voyager goes quiet. But it won't stop. Nothing out there to slow it down. It'll drift through interstellar space, past the Oort Cloud, past the gravitational reach of the sun, and in about 40,000 years, it'll pass within 1.6 light-years of a star called Gliese 445. Nobody will be listening. Probably nobody will know. And strapped to its side, that golden record will still be there. The greetings, the music, the heartbeat, a message from a species that looked up one night, decided to throw something into the dark, and didn't need to know if anyone would ever find it. The edge of the solar system isn't a place you arrive at. It's a long, slow goodbye. And the thing we sent to find it is still out there, getting quieter every year.